Hello everyone, and welcome to this video on finding the inverse of a function that's defined by an equation. Alright, so in this video I'm going to go over an example of, we're going to be given a couple examples where I'm given an equation for a function, alright, a one-to-one function, so that way the inverse will also be a function. Right, remember that, a function needs to be one-to-one in order for its inverse to also be a function. So we'll be given equations of one-to-one functions and asked to find the equation for the inverse function. I'll go over the steps to do that. And I also want to demonstrate in this video, show you guys a nice relationship between two functions when composing, when doing function composition with two functions that are inverses. Something very nice happens, and it's something that we'll use to verify that two functions are indeed inverses of one another. Okay. So my first page is an example, where again I'm given an equation. I'm asked to find the inverse of g of x equals 5x minus 1. Now that is a one-to-one function. In fact, I'm going to do, I know it's not on graph paper, but I'm going to do a very quick sketch off to the side, just very quick by hand, draw a little coordinate plane here. A little sketch off to the side. And I'll graph this function. It's a linear function, y equals mx plus b, 5x minus 1. That would have now I'm drawing a very rough sketch here. It would have a y-intercept at -1, 0 input, output -1, and have a slope of positive 5. Alright, so just one other point here. So like 1, 4, right? If input 1, output would be 4. Again, it's not great. Just doing a simple hand drawing here. Alright, and then it's just a straight line. There's g, right? The graph of g of x equals 5x minus 1. And you see how this passes, right? Even with this rough sketch, you can see it passes the horizontal line test, right? If I were to draw any horizontal line, it would hit the graph in at most one point, right? There aren't two different inputs that give me the same output, right? Every pair of different inputs gives me different outputs. So this is indeed a one-to-one function. So g is, function g is 1-to-1. And that tells me that g inverse exists, right? The function g exists, the function g inverse exists, okay? If it wasn't 1-to-1, then I wouldn't have a function g inverse. You could draw the inverse, sure, but it wouldn't be a function, okay? Alright, so the steps, right? How am I going to do this when I'm given, just this equation? All right. So first, if it's given in function notation, I'm going to replace that with the y, replace g of x with y. All right. Or if it's f of x, replace it with y. All right, so we have y equals 5x minus 1. Right, remember that g of x is just the output, right? So it's the same as y. All right, now be careful. This y is representing g of x, right? The outputs of function g. All right, so this y represents the outputs of function g. Now we invert. Now what do I mean by this? Remember, when you take the inverse, right? When you're writing the inverse of a relation or a function, all the inputs become outputs, all the outputs become inputs, right? Remember how the coordinates would switch, right? So like on my graph here, here's the point 0, -1, right? This is a point, an ordered pair in G. So in G inverse, you'd have the ordered pair, -1, comma 0, you'd have this point, right? Negative 1 comma 0. Same thing up here, right? This is the point 1, 4, right? That's an ordered pair in G. Input 1, output 4. You switch that around. So input 4, output 1 in the inverse, right? So 4, 1 would be on the inverse, and it would be again another line, right? Because what you have here is a reflection, right? There would be the graph of G inverse, and you can see this is a function, right? The blue graph I just drew, it passes the vertical line test, right? You draw any vertical line is going to hit that graph at most once. And if you recall from a previous video, the graphs of inverses are a reflection across the line y equals x. Right? Remember the graph of the line y equals x, I dotted it here. You know, if you were to reflect all these points across that line, you know, you'd get one graph on top of the other. So they should be the same shape, right? They're both lines. Now, yeah, I know I have a line with 2 points on it. I could write an equation for it right now using slope and all that, but write it in point slope form. But that's not that's not the point of this video, okay? Because I'm going to see an example after this where we don't have a linear function and we're doing the same thing. So when I say invert for the second step, I'm just saying switch x's with y and y's with x's in the equation. All right, so that will look like this. So instead of y equals 5x minus 1, right, I have x equals 5y minus 1, right? Every x I see, there's only one of them, becomes a y. Every y I see becomes an x. Now you got to be careful here. All right, this y, right, in this equation up in step 1, in this equation, y represents the outputs of function g. But when I switch them, when I invert them, in this equation, the y you're seeing represents the outputs of g inverse. Okay, so they are, yeah, they're the same letter, but they represent different things. This represents the outputs of g. This y represents the outputs of g inverse because I have switched all the x's and y's. Alright, so once you've switched the x's and y's, once you've inverted, you know, solve for this new y. Alright, solve for the new y, which would be pretty simple here. You know, here I would just, you know, if I were to solve for y, I would add 1 and then divide everything by 5. So you get y equals, you know, you'd have x plus 1 and then divide everything by 5. That'd be 1/5 x plus 1/5. Right, or x plus 1 in the numerator, all of that divided by 5 in the denominator, same thing. Right, you could also have x plus 1 in the numerator and then all of that divided by 5. These mean the same thing. Okay, and then, you know, write function notation. So this is it. I mean, I'm pretty much done. This is the equation for this blue line, the inverse. And then I just replace back, right? Then I just replace the y with, now remember, this y is not g, it is g inverse, or f inverse if we're dealing with f. So I replace the y in this new equation with its function notation, g inverse. So here we go. So instead of y equals, you know, 1/5 x plus 1/5, that's g inverse of x equals 1/5 x plus 1/5, or x plus 1/5. And here we go. This is what we were asked for, right here in the box. The equation for this blue graph I just drew up here. This point with and check it out. Look at these ordered pairs. Wouldn't these ordered pairs -1, 0 and 4, 1 be on this graph? Where if I plug in -1 for x, that'd be -1/5 plus 1/5. That'd be 0, right? The output 0, the y coordinate. When I plug in 4, that'd be 4/5 plus 1/5 would be 5/5, which is 1, and you see 1's the output. So this blue graph of this line is indeed the graph of the equation g inverse of x equals 1/5 x plus 1/5, or y equals 1/5 x plus 1/5. Alright, so great, I found the inverse. Now, there are very often, though, you're going to be asked to verify this result. All right, so very often after you find the inverse, they'll say, verify this, check it. And you've seen me in other videos if you've been watching this, my videos for this channel. You always check solutions, right? You always check your work. So how do we verify that two functions are indeed inverses? Right. Well, the way you verify it is through function composition. Right, and I've done a video before this on that. Look up function composition. Look at what happens with a function and its inverse. Right? If I compose them, say I compose G inverse with G. Well, take the number 1. If I take the number 1 as an input for G, that gives me an output of 4. And then I take that output of 4 and put it into G inverse, it takes me right back to 1. 1 to 4, 4 to 1. I ended where I started at the number 1. And that is the case for any input when you are composing inverse functions. And that's what I have for you here on the next page. Okay, so here's a nice relationship between inverse functions. One way is, if I compose f inverse with f, remember this little notation, the O symbol means f inverse composed with f of x, or f inverse of f of x. If you compose two inverses and the value that you're plugging in is actually in the domain of f, I would plug x into f, giving me some output, and then take that output, plug it into the inverse. Well, that would take you right back to x, because remember, the inverses, they just reverse one another. You just switch the x's and y's. So when you compose f inverse with f at any input, what your output is, what you're left with, is that very input you started with, just x itself. And same thing the other way around. If I compose f with f inverse, do f of f inverse of x, you should end up with the input you started with, because you'll plug a value into a function. Say I plug 1 into some function, it takes me to 4, and then I plug that number into the inverse and it takes you right back to 1, like I was saying earlier. So you should end up with just the input you started with. Okay, so this is how you verify that functions f and g, or f and f inverse, this is how you verify that two functions are inverses. Compose them in one order, compose them in the other order, and do you get the value of just x? Do you get the input that you started with, right? Just x both times. And this is actually one of those few cases where the order that you compose in will give you the same result. Right? If you watch my video on finding the composite function, you saw before that a lot of times when you do f composed with g and then g composed with f, you're getting different expressions. They're not the same all the time. But in this case, when f and g are inverses, they will be the same no matter what order you compose them in, and they'll both be equal to this expression, just plain old x. All right. So let's do that for this example. Okay, so what were my functions? They were, g of x equals 5x minus 1, and g inverse of x equals, 1/5 x plus 1/5. So I'll write those again on a separate page, and we'll go through and verify that they are indeed inverses. Right? Do those two, when I compose them, am I left with just the input I started with? Am I left with just x? Alright, so we had g of x was equal to 5x minus 1, and g inverse, well, maybe, right? We have to see if it's the inverse for real, equals 1/5 x plus 1/5. Alright, so let's verify that they are inverses. So one I'm going to take, let's do g inverse composed with g of x. I remember you could also write this way, g inverse of g of x. All right. So remember how this composition works. It's almost like from the inside out, or right to left. The number x, whatever the input x is, if it's in the domain of g, it goes into g first, giving me 5x minus 1, right? When I plug x into g, the output is 5x minus 1. So this gives me g inverse of, all right, and then, right, this guy here is 5x minus 1. All right, and then this output, this 5x minus 1, becomes the input for g inverse. So I plug this in to g inverse. So everywhere there's an x, right, everywhere the input is in g inverse, I replace it with this quantity 5x minus 1. So we have 1/5 times, and then instead of x, right, this quantity 5x minus 1, and then plus 1/5 after. And let's distribute the 1/5 here, simplify. Now 1/5 times 5x is just x, 1/5 times -1 is -1/5, and then plus 1/5, and look at that, -1/5 and the positive 1/5 makes 0, and you are indeed left with just x. So check mark on that. It works out that first way, in that first direction, but it's got to work in both. All right, so you have to do both. You have to do that and, okay, not or, not one or the other. Check the other direction too. When I compose g inverse with g, they reverse each other, they undo each other. X goes somewhere and then I get taken right back to x. But let's see if it works in the other direction as well. So I take g composed with what I think is g inverse. We'll see. And again, another way to write this would be g of what I think is g inverse of x. All right, so same deal here. Remember, the way composition works, you take the number x, whatever the number x is. If it's in the domain of g inverse, I plug it into g inverse. All right, and then what is that? Well, what does g inverse give me? When I plug in x, it gives me 1/5 of x plus 1/5. So this will be g of, and then g inverse of x is 1/5 of x plus 1/5. And then this is telling me to go to the rule for g and plug in the value 1/5 x plus 1/5. All right, so in the rule for g, wherever there's an x, I'm replacing it with the quantity 1/5 x plus 1/5. So instead of 5 times x, it's now 5 times this 1/5 x plus 1/5, and then you have minus 1 after. Well, distributing this 5 here gives me 5 times 1/5 x would just be 1x. 5 times 1/5 is positive 1, and then you have minus 1, and that is indeed x again. So check mark on that. It works in both directions, right? When I compose these two functions in both directions, they undo one another, and I'm left with the input I started with, right? It goes through the process and it takes me right back to where I started at the value of x. Same thing here. I plug in x and I get back x, all right, when composing these two. So noting both of these things, g of x and g inverse of x, I know I called it the inverse, but now we are truly seeing that they are indeed inverses. Great. And again, you have to do both, right? You have to do both directions. All right. So let me do one more example of this where I'm given a function. I'll make a quick sketch of it, and to show you that it's a one-to-one function, right? So that way the inverse will also be a function. Then I'll go through and find the equation for what we think is the inverse, and then verify by checking these directions, checking these compositions. Okay. So my last example here. Here's a function, f of x equals x to the 5th power, then plus 3. Now if I were to make a very, very rough sketch of this off to the side, I know it's not graph paper, I apologize. I'll do this here. So this would have 0, 3 on it, right? It would have 1, 4, -1, 2. And you know, being a fifth power, this would be, if you remember your power functions, you know, the y equals x to the first, x to the second, x to the third. It's like you know, an odd power function, right? X to the first, x to the third, x to the fifth. So it's going to have this like weird kind of S snaky shape look to it. Be very flat here and run through all these points and look something like this. All right. Again, this isn't great. It's a hand drawing. If you want to put it on a calculator or something, be my guest. Right. So there's, you know, the point 1, 4. Here's the point, you know, 0, 2, and the point -1. Sorry, 0, 3, and the point -1, 2. Right. And that's function f. Right. Now, if you wanted, you could graph what f inverse will look like, right, by plotting some points and keeping, you know, just remember reflecting this across the line y equals x. So like, you know, f has 0, 3, so f inverse will have 3, 0, right? There's 3, 0. F has 1, 4, so f inverse will have 4, 1. F has -1, 2, so f inverse will have 2, -1. And it'll be the same kind of shape, right, just reflected. And now again, this is a very rough drawing, rough sketch that I'm doing. But f inverse will look something like this. And you see it's a function, right? It would pass the vertical line test. And this should be a nice reflection across the line y equals x. And these point where they meet would be on y equals x, right? Now again, not perfect, but here's y equals x dotted in, and you can almost envision, hopefully, that, you know, the reflection property. Now that's pretty bad actually. Maybe this curve, this hump should have been more down here, but they should be a reflection across the line y equals x. All right, but enough of that. What we're trying to do is find the equation for this blue graph I drew here, this f inverse. All right, so remember how this worked. Remember this, I'm just going to replace f of x with y, right? So in this first equation, y will represent the outputs for function f, the red function. So y equals x to the fifth plus 3. All right, and then we invert. Remember what I said on the last one, where when I talk about inverting, right, writing the inverse, the equation for the inverse, remember the ordered pairs switch up. You saw on my graph here, 1, 4 became 4, 1 on the inverse. You know, 0, 3 became 3, 0 on the inverse. So every y you see in the original equation becomes an x. Every x you see, and there's only one of them here, becomes a y. So x equals y to the fifth plus 3. All right, and then we solve. Now in this equation, the y you are seeing represents the outputs for that f inverse of x, not f. Right? So the y up here represents outputs for function f. The y here represents outputs for the function f inverse. Right? Just be careful with that. All right, so this is solving for y. You got, you know, y to the fifth on one side would be equal to x minus 3. And then I would raise both sides to the 1/5 power, or take the fifth root of both sides. And remember, the fifth root of something to the fifth power kind of undoes one another. You're just left with y. And it's not like an even root, right? Remember, the square root of something squared was the absolute value of the base, right? We don't have to worry about that here with odd roots. You can take odd roots of anything. So taking the fifth root of both sides, we have y on the left equals, and then the fifth root of x minus 3, right, where x minus 3 is the entire radicand, all underneath the radical symbol. Or you could write this as, you know, x minus 3. Like I said earlier, you could raise both sides to the 1/5 power. Remember that relationship between fractional powers and roots. Both are fine. So I've solved for y, and then we can change back, you know, replace this y is f inverse, right? So f inverse of x is the fifth root of x minus 3. And this is the equation we're asked for. and double check, you know, I got some points up here, right? There was 4, 4, 1. How about if x were 4, wouldn't you get 1 as an output? Yeah, the fifth root of 1. If x were 3, wouldn't you get 0 as an output, right? And I've got 3, 0 on that F inverse graph, and so on. Right? But now let's verify. You know, I believe this is the inverse, but as always, you should check your solutions. Let's verify that these two expressions, these two functions, are indeed inverses of one another. So that's what the composition. All right, so like the last one, I'll write both of them up. Right, we had our original function was this x to the fifth plus 3, and then what I believe is the inverse was this fifth root of x minus 3. Alright, so the first one I'm going to do, I'll compose f inverse with f. And what I'm hoping to get is just x back, right? If these truly are inverses, then when I compose them in either order, I should get just x back, right? Start where the output should be where the input that I started from. Alright, so this is f inverse of f of x. Alright, and f of x, remember, is this x to the fifth plus 3. So this is f inverse of x to the fifth plus 3. And now I take x to the fifth plus 3, and that becomes the input for f inverse, what I'm calling f inverse. So I replace the x in this rule with the quantity x to the fifth plus 3. So this is the fifth root of, you know, x to the fifth plus 3 instead of x, and then minus 3. Now really there was no need for parentheses there because it's not being multiplied by anything or raised to powers. And then what is x to the fifth plus 3 minus 3? That's just x to the fifth. So I have the fifth root of x to the fifth, which I said earlier, these just undo one another, the fifth root and fifth power. That would indeed be x. Alright, so check on that direction. When I compose them in this order, they undo one another, and I'm left with the input I started with. I'm left with x. But you must also check the other direction, because I'm not going to get into it, but there are some examples that you can find out there where when you compose two functions, now maybe not after finding the inverse like this, like we did, you know, because if I go through this process and find an inverse equation, you know, there's a good chance that they are actually inverses. But you could find some examples out there of two functions f and g where, you know, f composed with g is equal to x, but then g composed with f is equal to something else. Alright, so just because one direction is equal to x doesn't mean that they're inverses, right? The other direction could be a different expression. So be careful with this. So I checked the other order. Let's do f composed with f inverse. Alright, so f of what I think is f inverse of x here. Alright, so x goes into f inverse first, which gives me this fifth root of x minus 3. So it's f of, and then again this expression in the parentheses here, f inverse of x is the fifth root of x minus 3. And then I take this fifth root of x minus 3, and that becomes the input for f. So instead of x to the fifth plus 3, you know, it's this to the fifth plus 3. I replace x in the rule for f with the fifth root of x minus 3. So it's the fifth root of x minus 3 to the fifth power, right? That's going in for x here, and then plus 3 after. And nice thing about, you know, the nth root of something to the nth power like this, with the nth power on the outside, they just undo each other. You're left with the radicand. That's x minus 3, this first part, and then plus 3. And oh, look at that, it is indeed x, right? The negative 3 and positive 3 would make 0. And I'm left with x. Great. It works in the other direction as well. So these two functions do undo one another in both directions when doing composition, right? F inverse composed with f, f composed with f inverse. So since it works in both directions, f of x and what I called f inverse, they are indeed inverses. Right, so But yeah, you must, and you know, if I know if you go through this process and you know you did everything right, there's a good chance that they are inverses already, and you usually don't have to do this. But very often in a lot of textbooks, a lot of exercises and exercise sets, quizzes, exams, whatever, very often you'll be asked to, after what you think you found is the inverse, also verify that it is indeed the inverse function of the function you were given. Great. All right, so just remember here that, trying to find the inverse of a one-to-one function, find the inverse function, just, switch all the x, replace all the x's with y, all the y's with x, and then solve for that new y, and that new y represents outputs of the inverse function, right? Not the original. And of course, you got to verify, right? Make sure that when you compose them in either order, you're getting back just the expression x, right? You're getting back just the input you started with. Great. All right, so just make sure you keep studying, keep reading, keep practicing, stay persistent, keep practicing, stay positive, and don't give up. And I know you can get through this. All right, I believe in you. And thank you very much for watching.